Hello friends, welcome to my channel. Let's have a look at a classic problem. Problem 250, count Univalue Subtrees. In this problem, our main solution will be based on recursion. So here first let's read through the short statement of the problem. Then we do a simple analysis when we write the code. So first let's look at the statement. So given the root of a binary tree, return the number of univalue subtrees. A univalue subtree means all nodes of the subtree have the same value. So here are three examples. So in example 2, so this tree is a null tree, so the number of univalue trees is 0. And in example 1, so the count is 4. For example, this one is 1, this one is also 1, and this one is also 1. So the three leaves are 3 univalue subtrees. Also, we can consider this one. So this one is also a univalue subtree. However, this root 5 does not represent a univalue subtree. The reason is that, so here we have a 1, which is not 5. So similarly, you can analyze example 3. So here the return is 6. So the additional assumptions or constraints for this problem are the following. First, the number of nodes in the tree will be in the range given by the closed interval 0 and 1000. So 0 says that the tree can be a null tree, and 1000 actually give us an upper bound of the problem size. Secondly, the range of the node value is in between negative 1000 and positive 1000, both end inclusive. So in other words, so the node value can be negative. So with that said, let's look at the method. So our main method or main thought is recursion. The reason recursion is natural for such problems is that the binary tree actually can be defined recursively. So our plan here is the following. First, we'll give a brute force solution to understand the details. So the process is to check if each node represents a univalue subtree or tree during the traversal. As for traversal, we can do what we want to do. So we can choose different orders of traversal or methods. So this will work due to the problem size specified by constraint item 1. So after that, what we're going to do is to write a pure recursion solution. So we are going to use a hyperfunction f to determine if a tree node represents a univalue tree with a given value. So here, in other words, we want to write a function f which takes a node and which is a tree node and a value which is integer as arguments or input, then returns whether this tree represented by the node is a univalue subtree, and with the univalue being the value given here. So during the process, actually we can update the counting of univalue trees. So that's our plan. So next we are going to go to coding, and in the process we would like to explain the logic and explain the code line by line. So with that said, let's first look at the first version of solution. So I'm going to call it brute force. So this can be done is due to the fact of the problem size. For this, first I'm going to define a hyperfunction called f_node. So in other words, we are going to check if this tree represented by the node is a univalue tree. So this is actually very simple. For example, if not node, so null tree, so we're going to return true. So in other words, we are going to return this null tree as a univalue tree. Actually, more to us, this is sort of a stop condition or base condition for recursion. So now, if node left, so we want the node left have the same value as the node value. So we are going to check if node left value does not equal to node value. So in this case, the tree represented by the node cannot be a univalue tree. so we're going to return false directly. So otherwise, so we're going to check if not, so node left. In other words, if the left subtree is not a Univalue subtree, then we're going to return false again. So this is the one case for node left check. So now let's check the node right. So if we have a right subtree based on the current node, then we're going to hope that the node right value equals to the node value. If not, so this tree represented by the node cannot be a Univalue tree, so we're going to return false directly. Otherwise, so if the value of the node and the root of the right subtree are equal, then we're going to check if the right subtree is a Univalue subtree. So if not, f node right. So in this case, we are going to return false again. So if we can pass all of the cases to if condition check, then we are going to return true. In other words, so the tree represented by the node is a Univalue tree. So this is actually the first step. So in this version of solution, so we write a function, write f to check if node represents a Univalue tree. So this is very brute force in some sense, but it's good for us to really understand the problem logic. So next, we're going to do a traversal, right? So for this, actually, we can do whatever traversal we want. So first, I'm going to treat a special case, that is the null tree case. So if not root. So in this case, I'm going to return 0. So per the problem requirement, or as you can see from example 2. So next, we're going to do a general traversal. So here, I'm going to use depth first traversal. Let's see. We're going to put the root into the stack, and then we do the while loop. So while stack. Then we're going to get the node as stack pop. Then we're going to check if this node represents a valid Univalue tree. So we're going to check. So actually, we are going to increment the result. Let's initialize a result. So here. So here, if not root, we can return result, right? So otherwise, we'd go to next. So here, we're going to increment 0 or 1, right? So f node. In other words, if this node represents a valid Univalue tree, so we're going to increment this result variable state by 1. Then we're going to do, if we do not have this line of code, actually it's just a standard traversal. So then if node right, so here I'm writing first the node right. So then we're going to do stack append node right. So then we check if node left. So we're going to do stack append node left. So this is actually very standard. So after we finish traversal, actually we finished update the state of the result variable, and then we are ready to return the result. So this is the first solution format. The reason we write this solution format is just for understanding the detail of the problem or digest the problem requirement. So in the process, actually we also practiced the one version of traversal. So with that done, let's first do a special case check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the test cases. So this is the one version of solution. But when we do the check, actually there are a lot of redundancies. So let's do another solution. So here I'm going to copy this function signature and change this one to be version v1. So now let's write this second version. So the second version is pure recursion. So here I'm going to write a hyperfunction. So then we are going to increment the counting of Univalue trees in the process when we call the hyperfunction. For this purpose, I'm going to initialize a result. So this is the the variable we are going to increment. So we are going to write a nested function. That function is called f. Let's see, it accepts a node and a value. So the return is, we are going to check if node represents a univalue tree with the univalue being value. So this is the function. So here a note is that during the process we also update the result variable. So that's our thought. So now with that said, let's first do because we want to update this result variable, we first need to make it non-local, right? So this is standard. So next we're going to check if not node. So in this case, so we're going to return true. This we can more or less regard it as a stop condition, right? So this is very special, right? So next, so we're in this case, so we return true, but we do not increment this result. So next we're going to check if the two subtree, if they exist, so is with node value being this one. So this also verifies this return is reasonable. So if both the two conditions, let's see, if f node left and node value. So notice that this f node, it can be empty. So if it's empty, so we regard this function returns a true. So no matter what value we put. But if it's not null, so then we want this node this tree has a value being the node value, right? In other words, the parent. So this is one, and another one is f node right and node value, right? So this is what we hope. If not, right, so we are going to return false. So this is the case. So if after this if check, so nothing returned, so this tree represented by the node is a valid univalue tree. So we're going to increment our result by 1. Then what we want to return actually is also a node value if it equals the given value. So here this return basically checks if the node is a valid univalue tree. We are going to update the result. However, for the return, we want this univalue tree to be with the univalue being this value in the argument, right? So that's why we first do this. So then we do this. So this is the hyperfunction, right? So what we are going to do next is we call this function. So we can call this with the root, and then we put a value here. So here actually we can put any value. So but there's a detail, we cannot put a root value. The reason is that the root can be null, right? If it's null, so we put a root value here. So null objects has no attribute for this. So let's put anyone. So actually, so here because it's in this one, so I can put this a smaller one. So let's see this, but this you can put a 0 any number. So then we can return a result state. So that's the second solution format. So with that done, so let's first do some check. It passes the first example. Now let's look at the generic case. It passes all the generic cases. So with that done, I guess, so we presented the two formats of solutions to this very classic problems. So here actually we want to comment. So this problem can be solved by a variety of different ways. You are welcome to try to modify the code or come up with other solutions, but all in all, it's crucial to really understand the logic of the problem. So with that said, we finished the practice. Thank you.